Well, let's talk about the natural base E. So the natural base E actually was named for Swiss mathematician Leonhard Euler. The reason why it is he computed this to 23 places. But E is an irrational number. It equals 2.7182188, on and on and on and on. It's a non-repeating, non-terminal decimal, therefore it's an irrational number. But this natural base and its inverse, the natural log, ln, is actually what is used most often in real-world applications when it involves exponential functions or logarithmic functions. And so we need to get used to natural base E, or the log naturel, the natural log, which we'll get into when we take up logarithms. But for right now, we're in exponents. So here we go. So we're looking at transformations. If you look at the blue here, this blue graph is the graph of e raised to the x power, the exponential, where the exponent is in the variable of this natural base e. And then we're asked to look at q of x equaling e raised to the negative x power. Well, of course, this negative in this exponent, we really could actually write this as 1 over e to the x power. That's what that negative does. It puts e to the x into the denominator of a rational function. And because of that negative, we see a rotation, a flip, if you will, across the y-axis. It's flipping it across the y-axis. We still have a y-intercept there at where x is equal to 0 and y is equal to 1. The y-intercept there at 1. But we see that it flip across the y-axis. We're going to look at a couple more, but the next one actually I'm going to, after we kind of get an idea of what's going to happen with it, I'm actually going to graph it on the calculator, make sure we got our keystrokes down in order to do that. All right, so again, we're going to compare the graph f of x equal e to the x power to r of x, which is equal to e raised to the power of x minus 5. And this negative 5 sitting out here, not in the exponent, not as a coefficient, is going to give us a vertical shift down, a translation, vertical down by 5. So why don't we go to the calculator, we'll graph both e to the x and e to the x minus 5 and look at that comparison. All right, well, here we are over on the calculator. And we can find the e in two places. One, if I look above the division symbol there in blue, I see e, and that's actually the natural base. But if I am actually graphing exponential functions, the second place is probably where I want to look, and that is, if I look next to the 4 key, to the left of that, I see ln, that's the natural log, it's underneath actual log, and then I see e raised to the power of x. So I can hit second ln, or e to the x, and just put an x in the exponent. And then we're going to graph the transformation. So again, I'm going to hit second ln. I got the e. I put in the exponent, and then I go negative 5. Let's take a look at those graphs. Now, the e to the x should just look like a regular exponential function. It should be coming in, hovering along the x-axis on the negative side of the x-axis until it gets near the y-axis. We should see it cross there and have a y-intercept at 1 and then rapidly ascend. And then we should see this one do the same thing, except it's going to be 5 units down on the y-axis. Let's see if that's true. There comes our first one, swooping along. There comes our second one. And let's see, I had a vertical shift down by 5. And so that's going to put my y-intercept at negative 4. because my y-intercept originally is at 1. 1 minus 5 is negative 4. And so there we see that transformation. And also, again, I could use the E above the division symbol, and then I'd have to do the caret X, or I can just simply save myself that by hitting second LN, and it's going to bring up the exponential of the natural base. All right, well, let's look at a third transformation. And here we've got, of course, in the blue, we got f of x. And then our transformation t of x is 3 times e raised to the x power, or the natural base raised to the power of x. And this is going to give us a dilation or a stretching of the graph. And then, interestingly, what do we see here with the y-intercept? Well, originally it's at 1, and now it's at where y is equal to 3. But we're multiplying 3 times the natural base raised to the power of x. And so the x-intercept then is going to become, again, if I put e equal to 0, where x is 0, well, that's 1, and 3 times that is 3, and that's how I would find the y-intercept by setting x equal to 0. So here we see a dilation of our exponential function.